Halo, tes, 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 tes. Mas Adan, suara saya masuk nggak? Oke,
Terdengar, Pak.
thank you. Thank you, Pak. Makasih.
Hello, Viveka. Hello, Viveka. Hello.
Ya, halo Martin.
Okay. Good afternoon.
Good afternoon.
Thank you for the webinar. Yeah.
Yeah.
So just waiting for 2:30 so we can start it. Okay.
Yes, yes.
But it seems that the time is not too much. What happened?
Usually, times are being so they actually because we tell them the 1:30, so usually 1:30 more will come.
OK，大点声，我听不见了。OK，我那大点声。我这边连那个麦。OK。So let me keep silent and waiting until the 2:30.
Okay. 1:30.
Oh, 1:30. Sorry.
Yeah.
I'm talking about the Beijing time. Yeah.
Yes. Yeah. No different.
Okay, yes. 1 hour different. Yeah.
Okay.
Excuse me, Mr. Zulfikri. Hello?
Yeah, Martin.
Yeah, can you see the screen?
Yes, I see.
The
No.
PPT introduction, PPT, right?
Yes, I see.
Okay, good.
Okay.
Recording in progress.
Excuse me, Mr. Zulfikri.
Okay, maybe we can.
Do you need to present your laptop screen to the attendees?
I think we just open and then start the webinar.
Okay.
I will tell the rule and then short speech and then you start the introduction. Yeah? So we have the schedule. I will introduce the attendees and then I will guide the
那个参会的人不能
Okay, Martin.
Yes.
Okay. How if we start now?
Yes, no problem.
Okay. Bismillah. Assalamualaikum warahmatullahi wabarakatuh. Selamat siang, bapak-bapak, ibu-ibu, rekan-rekan dari para praktisi ya, Teknik Sipil seluruh Indonesia. Hari ini kita ketemu lagi di webinar Testindo, mungkin yang ke-12 atau yang ke-11 ini saya rutin melakukan aktivitas ini untuk sharing ya. Hari ini Testindo kita ngundang dari prinsipal di TCC, ini perusahaannya di Kanada, cuma dia punya office di Beijing. Jadi kita akan bahas tentang seismic ya. Ini metode geofisika, juga disebutkan juga di SNI Geoteknik ya. Ada beberapa metode ya untuk soil investigation. Dan metode seismic ini relatif sangat terbatas gitu ya teman-teman, mungkin yang mengenal karena memang di kampus gitu nggak termasuk pelajaran mungkin ya. Makanya kita ingin sharing, dan hari ini saya ada dua speaker ya, saya coba share ya. Ini speaker kita. Sorry Martin, I would like to share my screen.
Okay, so I can start my introduction now.
No. Just I would like to introduce the speaker first.
Okay. I'm the first speaker. Yeah, and the second is analysis.
I mean, I have a PowerPoint to introduce the. You just stop your screen first. Then I would like to share my screen.
You want to present the picture for the webinar, right? Let me check.
I just share the keynote speaker CV.
Wait a moment, please.
Okay. I would like to. Hello Martin, I would like to share my screen. Oke, nggak apa-apa, ini juga udah kelihatan ya, bapak semua. Ini ada Alan Su sama Wei Hong Yu ya. Ini di PowerPoint saya ada sih. Jadi speaker kita ada dua. Alan Su ini dia bachelor degree dari China University of Petroleum, dia geofisik ya, tahun 2011. Dia master degree dari Institute of Earthquake Forecasting CEA di 2014, dan terlibat dalam pengembangan microseismic processing software di perusahaan namanya Geotomo selama 2 tahun. Nah, dari tahun 2017 dia bergabung di perusahaan di TCC ini, mengembangkan algoritma processing dari seismic data gitu ya. Nah, yang Wei Hong Yu ini juga bachelor degree dari China University of Petroleum di geofisik, dan master degree-nya dari Institute of Earthquake Forecasting di CEA, kayaknya di Amerika ini. Terus terlibat di development microseismic processing software di satu perusahaan namanya Geotomo, dan juga dari 2017 dia terlibat dalam sinyal processing ya dari Seismic ini sendiri. Jadi backgroundnya ini spesialisnya dia di geotechnical, seismic dan disaster. Wei Hong Yu ini, kalau Alan Su dia seismic nota system dan teknologinya. Jadi kita nanti hari ini kita akan sharing selain tentang produknya juga ada case study ya. Jadi nanti kita akan share pertama Martin ke presentasi tentang perusahaannya, lalu ada informasi edukasi ya tentang likuifaksi, soil investigation, lalu ada case study. Case study ini case study likuifaksi, case study yang lain ya terkait penggunaan seismic ini. Dan sebenarnya kita biasa 1,5 jam, tapi kalau misalnya nanti teman-teman berminat detail ya, silakan sampai jam berapa aja kuat gitu ya. Terus nanti kalau perlu detail yang spesifik, kita juga di Tesindo ada tim. Kita bisa nanti buat sesi khusus kalau memang ada teman-teman bapak-bapak, ibu-ibu yang ingin kita bahas secara per kasus gitu ya, per kasus atau ada solusi ya tentang soil investigation baik dengan seismic maupun yang lain. Okay, from PT Tesindo only a short introduction because I would like to benefit your time, everyone. I would like you to be happy to get the new knowledge and also engage in this webinar. And now is the presentation from Martin Q. So Martin, please start your presentation.
Okay, thank you. Okay, thank you.
Yeah, welcome.
Okay, good afternoon, everyone. Welcome to the webinar. And at first, I want to just thank Tesindo and Mr. Zulfikri to organize and even to host the webinar for us. And also, thanks for everyone for your time to participate in our webinar at this afternoon. And I'm grateful for everyone's support. And my name is Martin from Smart Solo DTCC company. Actually, Smart Solo is our brand, and my position is overseas marketing and sales manager. So in the beginning, we will have 3 speakers today from DTCC company, and I will just take around 5 to 10 minutes to make a brief introduction on our company and product. And after that, our senior technicians, Alan Xu and Mr. Wei, will give us some more details from the technical yeah. So let me just try to start my first presentation. The introduction of our company and the product. So as everyone see here, and our company name is DTCC, Dynamic Technology Company Limited. And we founded in Calgary, Canada in 1999. Yeah. And over past 20 years development, we have more than 260 employee, and have a full branch office located in different countries in the world, and also have some facility in China. So let me just introduce one by one. So as this page shown, our headquarters still based in Calgary, Canada. And it was founded in 1999. And now we have a commercial center based in Beijing, and just the place we are based now. And the commercial center based in Beijing responsible for global sales and technical support. We also have a 2 production facility. The first plant located in north of China, Langfang City, and it produces geophone product. And the second plant located in south of China and Dongguan City, next to Shenzhen. It produced a nodal seismic sensor system. Yeah, and as well, we also have a R&D center based in Shenzhen City. After this, we also have a 4 branch office located in different countries. The first one is Houston, USA. And we have a local employee based in there to in charge of the American continent business. And the second one is Moscow, Russia. And the third one is Jakarta, Indonesia. And we have an employee based in there. And Sadan is just on the presentation list. Yeah. And the fourth one is Cairo, Egypt. Yeah. And the next page is about our product. So what we supply, and the product name is nodal seismic sensor. And it contains a different kind of node sensor. And the first one is IGO 16 HR. That is a single 1C node sensor. A second one is 3C IGO 16 HR. And the third one is IGO BD3C. This is a broadband node sensor. And the fourth one is IAU 19 HR. And that is available to connect with the external geophone stream product, to make it match with a different kind of terrain, like marsh or even shallow water. And the last one is MU3C. This is a new product we just launched at this year, and it's also to connect the external 3C geophone stream product, which is popular for geotechnical survey area. And the advantage of Smart Solo is they have three significant features. The first one is highly reliable than the conventional geophone stream product. And second one is low cost. It's much cheaper than the geophone stream product, the first generation seismic sensor product. And the third one is a better HSE performance. Yeah. So for each item, they also have some detailed information, but because due to the time limited, so I can just introduce details at the webinar. So if anybody just have an interest in this part, so we can have a further discussion after the webinar. Yeah. And the Smart Solo is suitable in various environment. For example, in dense forest and urban area, and gobi environment, and snow area, and even in desert and in water and swamp area. Yeah. So until now, so we already delivered over 350,000 channels Smart Solo node to over 30 countries clients, and especially in Indonesia, we already delivered over 10,000 channels of IGO node sensor. Yeah. So our client include ANALISA, include ITB, yeah, and even some other private company client. Yeah. So this is our client, a part of a client, include Danson, ANALISA, BGP, even some our competitors from America, like Innova. Because we also have as what I introduced, we have a plant, a production facility to produce the geophone element product. So our competitors like Innova, Field, they also will just purchase the geophone high sensitivity geophone element from us to equip in their node sensor product. And even some client from America like Ares, the world most famous earthquake monitoring platform. Okay, thank you. So later, I will just invite our senior technician, Alan Xu, to give us some introduction on seismic method. Yeah. So welcome, Alan. Yeah. Thank you, everyone. Yeah.
Hello, everyone. Hello, my friends in Indonesia. My name is Alan. I'm very glad to be here today to deliver my speech about introduction to seismic methods in soil engineering and structural health monitoring. Before I start, I would like to deliver my thanks to all the authors of my materials You know that most of my pictures in this report are not generated by myself. All the formula, equations, and principles are not invented by me. Some contents of my slides are from other researchers. So I appreciate all the authors. Thank them. My speech includes 3 parts. First, soil liquefaction. Second, seismic methods in soil engineering. Third, structural health monitoring. By the way, I prepared around 80 slides, so it nearly takes about 1 hour. Yeah. So what is soil liquefaction? Generally, it's a kind of seismic trigger hazard. It happens in water-saturated sandy beds near river banks, bays, and coastal areas. The ground becomes soft, behaving like fluids, and loses its bearing capacity to support buildings on it. It causes damage and buildings and losses of lives. Here are the consequences of the liquefaction. Just imagine when you stand on the ground, when the ground suddenly becomes affluent like water, you will lose the support of the ground. What happened to you? That is what happened to all the buildings or structures on the ground. Here are the several typical consequences led by liquefaction, like sand buoy, flow failure, ground sediment, ground oscillation, lateral slide. All these consequences lead to bad results to the structures on the ground. So what is the mechanism of the soil liquefaction? There may many factors affect the soil liquefaction, but the mainstreaming think that the main reason of occurrence of soil liquefaction is the effective stress go down, and that it can be caused by the member triggering, like seismic waves. Here is a picture to illustrate what happens when the strong seismic energies propagate through the sand. The picture shows us that the reformation of the sand structure. Just imagine here we have an empty area and it is filled with the water. If just a grain of sand fills that area, then the water will be split out and the pore pressure will be increased, and that lead to the decrease of the effective stress. When effective stress decreases to a critical level, the material transforms from a solid state into a viscous state, and the liquefaction has occurred. Here's a brief chain to illustrate how the earthquake occurs can influence the happening of the soil liquefaction. The basic idea is that earthquakes occurs and a seismic wave can influence the sand structure, and that causes the increase of pore pressure, and so that the effective stress of the sand decreased. Okay, now we have known the basic reason of the soil liquefaction. What can we do to prevent this kind of hazard? How to predict the vulnerable area? Here, I pick up a paper, and the paper used several parameters to calculate a map, and that map can help us to identify which area is more vulnerable and more prone to be influenced by liquefaction. Here we have 4 parameters. First is the shear velocity 30. Shear Vs 30 means the velocity of shear wave within 30 meters depth. Second is the water saturated state. It can be calculated by the complete terrain index. Third is the geological age. The fourth is the earthquake's influence. The below equation is the method we use used by the author to calculate the map. And there is a critical value y0. When the y is larger than y0, it is easy to be liquefied. If it is less than y0, there will be no liquefaction. This is the basic idea for the researchers to study the area along the coast, along the river. Yeah. Here's the result. The left picture is a study about the earthquake happened in 1978, and that caused a vast area of liquefaction. The right represents the area which have occurred liquefaction. The right picture is calculated by the author with his methods. We can see clearly that the area predicted by the author comply with the real situation. So this method works well for us to predict the vulnerable area. Here is another result. Here is a difference. The right figure is the real situation. The left figure is a prediction map calculated by the author with his method. We also can see that the prediction result covers well with to the real situation, which again proves that his method is efficient and effective and efficient. So we already know that the author uses 4 parameters to predict the vulnerable areas. So how can we get these basic parameters used in generating prediction maps? My answer today is Seismic. Here is a little derivation about the equations. The first equation we have shown that is effective stress is equal to total effective minus pore pressure. And the second equation, chain, the very last one, tau, means the shear stress. The capital G means the shear modulus, and the E means the shear strain. The mu is the Poisson ratio. So the shear stress is equal to Poisson ratio times the effective stress. Here we can make a conclusion that the shear modulus is directly related to the effective stress, and that is influenced by the shear velocity Vs. So the variation of the Vs can directly reflect the variation of the strength of the soil. It means if we know the distribution of shear wave velocity across an area, and we'll have a well understanding about the strength of the soil. Next, I will introduce some conventional methods to acquire soil shear modulus velocities or shear wave velocities. Here is the conventional methods to measure the sand. We also call it in situ test. We have many types of in situ tests like SPT, CPT, DMT, PMT. I think these methods are familiar to the civil engineer. To be honest, I'm not familiar with this test, but the basis of this test is to come to a specific spot in the field and drilling a hole and put the equipment in the hole and get some basic parameter and measure that physical quantity and then to derive some parameters we want. The left bottom figure is Indonesia, and the red cross, the blue cross and the red bonds is the real spots that where the institute test has been conducted there. From this figure, we can see that for the area with dense spots, and we can have a aware understanding about the soil properties there. But with for the blank area, empty area, we have no institute test there, so we won't have any. We won't have detailed information about the soil properties there. That's the problem. So that's also the defect of the conventional methods. Here is the figure to show that how we calculate the shear view modulus from the institute test parameter under different types of institute test. And again, it proves that shear modulus also be used by the civil engineer to study the soil properties. Here is the summary of the features of institute test. High cost. Here I say high cost. It is related to a situation that if we want to conduct a large areas investigation, we have to implement many institute tests that will cost much time and expenditure. So as I say, it can be low efficiency. In another situation, if we have limited money or limited expenditure, we cannot have many institute tests across the whole large area. So that causes the limited spatial extension of study of the soil property. The last one is reliable data. That's the most beautiful one of the institute test feature. I know that's the institute test feature can provide us the reliable data. And that is very useful for us to verify the seismic profile. So what comes to my mind is that comparing in-situ tests and seismic methods provides an efficient and cost-effective way to do soil properties investigations. Here is my economical equation. If we do some in-situ tests in some particular spots, that can provide quality control. And in other areas, we can implement large area nodal seismic investigation that provide a spatial extent. And combine these methods together, we can have a cost-effective soil property survey solution. The next, I will introduce mainly about the seismic methods for acquiring soil quality. Here means the physical quality like the P wave velocity, S wave velocity, and also the layered model. And I will introduce mainly focus on the principles about these methods. And later, my colleague Wei Hongyu will introduce some real applications. So I have three methods to introduce. First, surface waves. Wave is a quite useful and convenient methods for us to investigate the near-surface S-wave velocity model. And that can predict the compactness of the soil and also derive the shear modulus. Based on the source type, we can divide the surface wave methods into two types. One is active seismic. That means we use a source. The other is passive seismic. Passive seismic means without using the source. Generally, we we are familiar with a method name called MASW. And also we are familiar with a name in passive seismic SPEC, which invented by a Japanese geophysics scientist. And also we have different names for the people in different regions. Here for passive seismic. For the North American, they call passive surface wave. For the people in Japan, they call it micro tremor. Now for European study researchers, they call it ambient vibration. Here's the cartoon. I want to tell what is the surface waves. Here, the left cartoon, we have 2 layers model. First layer's thickness is 3 meters, and the second layer is extended into the infinite. The source type is explosion, and the resource receiver distance is 20 meters. Here is the source, and the green point is the receivers. And we can see the source generates 7 types of waves. There's one strong energy propagated along the surface. That is the surface waves. So the surface wave means that the energy mainly propagates along the surface. And the right picture is the seismic record. We can see the features of surface waves is that it is dominant not energy in each trace, and along with the distance increase, the waveform extends in time axis. I summarize up some features of surface waves. Wavefront, it is the cylindrical surface. Particle motion is the ellipse in counterblock direction. Amplitude, it decays in depth in exponential ratio. Phase velocity depends on frequency. This is the main feature of the surface waves, and which we use to inverse the S velocity. The last feature is the sampling depth. High frequency is samples the shallow layers. Low frequency is samples the deep layers. I mean sample means it will influence. It will record the velocity of that layers. The left corner, the last bottom, I show here is the decay of the amplitude of surface with the depth. And the right figure is the ellipse, the particle motion form is the counterclock direction ellipse. So in this slide, I want to introduce how can we get the S velocity from surface waves. Last slide, I mentioned that surface waves have a feature we call dispersion. So that's the basics we use to measure S velocity. So what is the dispersion? Dispersion actually can be explained in frequency domain. The surface waves can be composed of different frequencies of energy, and each frequency energy propagates along the surface with different velocity. So in the middle, the figure, the y-axis, the phase velocity, is changed along with the x-axis, which is the friction axis. So why can we measure S velocity with dispersion curve? The bottom figure is a sensitivity kernel. We can see that the dark area is with a large value. That means it's most sensitive to this part. It means that the shallow layer, the velocity, S velocity of shallow layer is more influential to the phase velocity of high frequency, and the deep layers S velocity has is more influential to the phase velocity of the low frequency on the dispersion curves. That's the basics we used to get the S velocity. Here is the sensitivity we calculate is the derivative of phase velocity over the velocity of the s velocity at each steps. Here's a quite familiar formula to all of us. We study it in elementary school. When we want to calculate the velocity of something, we should have two parameters. One is the distance, the other is the time. Here, in surface methods, the distance is determined by the station geometry. The travel time is determined by the phase shifting measurement. Phase shifting measurement, here I illustrate that in this equation. Dirt means the phase residue. Omega means the phase velocity. So we can calculate the travel time of surface waves. Phase velocity curve reflects the average velocity model beneath receiver array. Here is the concrete steps to work out S-wave velocity. First, we need to deploy the station in the field and record the seismic data. And then we collect seismic data to the computer and calculate the dispersion curve. And last, we do inversion job to get the final result, that is S velocity. Here is the field survey geometry for active seismic. We generally use hammer or width drop and with a linear array with about dozens of stations to record the seismic data. Generally, the array is deployed with equal distance to each other. Here is the real project seismic data recorded generated by a source. We can clearly see the dominant energy, that is the surface waves. There are many methods to extract dispersion curve from active seismic data. And the basic idea is to measure the phase shifting of a specific frequency. And also they can be transformed to each other with some transform theory. I will not show the details here. Here's the passive seismic field survey geometry. Being different with the active seismic, the passive seismic surveying geometry can be many types of arrays. It can be linear array, triangular array, L-type array, or circle array. All these types of array is to ensure it can record well the energy from different directions. Because we have an assumption that the Earth is a 1D layer model, so the energy from different directions is the same. So that is the basis of our current CRV methods. How to extract dispersion curve from noise data? Apparently, we cannot see anything in the noise data. It's just like a rainbow addition of seismic energy. But in fact, there are many surface waves in it. And generally, we use SPEC method and to extract surface dispersion curve. Here's a brief introduction to SPEC method. The basic idea is to calculate the coherence curve with stacking of the data. And the coherence curve is equal to the Bézier function. The independent variable of Bézier function contains the dispersion information in it. So by comparing observational coherence curve with the theoretical Bézier function, we can derive the dispersion curve. After we get the dispersion curve, how can we get the S velocity model? That is the theory related to the inversion. Here we have a layered model with multi-layers, and in each layer we have physical quantity like SV velocity, PV velocity, rho, that is the density of rock, and h means the thickness. Generally, these parameters can be related to each other, and we can write them within a function, with a implicit function here. And here we define the CR is the phase velocity as the independent, a dependent variable, and all the other matter is the independent variable. And the first step is we should calculate the sensitivity between the dependent variable phase velocity over all other parameters. That is the independent variable. We also call these derivatives the Jacobian matrix. Second, we build a linear system. J means the Jacobian matrix. Delta X means the model disturbance, and the delta B means the data residue between theory and observation. At last, we should do model updating. That is based on that in a small scale, the problem can be seen a linear problem, and we can update the model disturbance, and that will lead to updating of the that will lead to a minimizing process of the data residues. So with the iteration methods, we can finally get a converged solution that is updated as velocity of the layered Earth model. Here is a real application obtained by surface wave methods. It is a dam foundation investigation. From this figure, we can clearly see underground where is the weathered soil, where is the heavily weathered soil, and where is the water saturated soil. It's very useful for the engineers to do further decision about the structure on the ground. Here is another application of surface wave methods. It is an application to do survey about the river bank. Here I want to mention is that in the upside figure, we have 4 drillings, and with the drilling test, we can have a good verification to the S velocity we get from the surface wave methods. And under the verification of the drilling test, we will have much more confidence with the areas without drilling test. That's the fundamental strategy for geophysics, for the seismic exploration, and to solve the issues of multiple solutions. And that is also the soul of the seismic exploration. That means only with the seismic profile, it's not confidential. We may be not confidential to the result, but under the verification of some specific drilling, we become more confident to the result. And also the risk model can be verified by the geological column, and that's quite typical in civil engineering. Next, I'm going to introduce refraction. Refraction also a geophysical phenomenon. It can help us to get near surface PV tomographic velocity model. Here is the field theory geometry. It's similar to the surface view. We need a hammer and a drop with drop. Also, we have linear array. Here is the left figure is the real recording about the refraction exploration. Here I want to mention that in refraction method, we only use the first arrivals in general refraction method. And the right figure clearly shows that the three types of waves. The green one is direct waves. The red one is refracted waves. The blue ones are reflected waves. Ray theory is a quite important theory when we considering the wave propagation through the Earth. Here we will have a concept of wavefront and a ray path, and also the figure below. Different colors represent different types of waves. Red represent direct waves. Green is reflected wave, and blue is refracted wave. Here they pass through different, their paths are quite different. For the blues one, we can see the energy firstly propagate down to the layer, and when it encounters the layer, it will propagate along the layer, and then it will propagate upward to the surface and recorded by the receiver. It's quite typical ones. And what we use is this part, the refracted wave propagate along the horizons of the rock, and it will sample the velocity of that layer. Narrow laws is very quite basic law which we have studied in elementary school. This law describes a theory that the wave propagate from one layer to another layer, and the value, the sign of the incident, the sign value of its incident angle over the velocity of that layer should be equal between each layers. Here, the conditions of occurrence of a refraction is that the velocity of the deep layer should be larger than the velocity of a shallow layer. That's a condition, because when the incident angle increases, the transmitted angle will also increase until it reach 90 degrees. 90 degrees is parallel to the horizontals. It propagates horizontally. And that is refraction waves. And also we can calculate the critical angle over this according to this principle. Here is the geometry. We used to do the equation derivation in next slides. We have two layers. We have thickness each one, and we have source and receiver distance, and S critical denotes the critical distance. Here, critical distance is a critical point that over larger for the distance, source receiver distance larger than that, we can record the refraction waves. For the receiver distance less than critical distance, we cannot receive the refraction waves. Here we can derive the critical angle and critical distance by the Snell laws. Here are the 12 times equations derived for direct, reflect, and reflect waves for RG 3D layer model. The first is a direct wave. It's a straight line, and the slope is the velocity of that layer. The second is a reflect waves 12 times. It is a hyperbolic curve, and the last one is reflection traveling time. And that also is a line, a straight line. The slope is a layer, a PV velocity of that layer. Here is a figure I want to illustrate that how can we get the properties of each layer. Here we have two layers, and we can see from the left bottom there is a straight line which we can calculate that slope, and that is the velocity of the first layer. And also we can have a second straight line. That's the slope of the line is the velocity of the second layer. And the cross point we can calculate the critical distance. With all these three parameters, we can calculate the thickness of the first layer. Here is a more complicated situation. We have 4 layers, and the black lines in the left figure is the path of the refracted waves through each layers. And also in the right figure, we can see the 4 straight line. And also based on the what I mentioned, that calculate the slope of each line, we can calculate the velocity of each layer. And also this is the final equations we deal with the more complicated models. And first we need to calculate the intercept of the straight line, and then we calculate the thickness of each layer, and finally we calculate the velocity of each layer. Here is real project, which we will use to illustrate the method we just derived. The left one is, we can see the red line is the taking of the traveling time of refracted wave traveling time, and based on this red straight line, we can calculate there are 3 layers, and we can calculate also the thickness of each layers and their p-wave velocities. Here is a more colorful results that conducted by Professor Liu Lanbo in America, and on the top is the field, and the second, the figure in the middle, it shows the repass of refracted waves, and the figure in the bottom is a result from the rebased travel time tomography. Quite apparently, we can see the whole scenario underground, and where is the high velocity area and where is the low velocity area. Here, I want to deliver just a little theory about the rebased traveling time. Actually, with the method we just mentioned, we can have a well estimation about the properties of each layer, like p-wave velocity, thickness, and other information. But if we want more, we can do further. It is the rebased traveling time tomography. It can give a more smooth model. And the basic theory of tomography is like this. First of all, we should do a diversion of the Earth model. For RD model, we can divide it into different blocks. And also we have to set each block of p-wave velocity and other physical quantity. And then we can calculate the repass, the travel time of a specific repass. And also we can derive the disturbance of the traveling time corresponding to the disturbance of the p-wave velocity of in each blocks. And finally, we will build a linear system in the right bottom column here. And same with the method of inversion of surface wave velocity. We also use we can use many methods to update the model. For example, standard least square solution, diameter least square solution, and also iterative methods. All these methods can suitable to different situations of the problems. Here is what I want to show an example with the reflection exploration. The project happened in central Japan and is to build a tunnel underground. In the left top figure, we can see the straight bright black line as a tunnel. The problem the contractor encountered is that the cutting face collapsed during the construction of the tunnel. So the contractor needed to know the whole situation of the soil, so they need to so they can make further decisions about how to design their tunnel, if they need to turn their tunnel, something like that. And the result given by the reflection method clearly shows the distribution of the PV velocity underground. And for green, it means the low velocity zone. For the color white, it means the high velocity zone. And it successfully predicts the vulnerable area for the whole hills. Next, I will introduce the reflection methods. It provides stacking methods, a stacking image, which reveals layered Earth model. Seismic reflection is the most widely used geographical technique. It can be used to derive important details about the geometry of the structures and their physical properties. The basic principle of the reflection method is that we want to get a 0 meter offset reflection image. That is to say, for once the figure below is the Earth model and the figure upside is the sensitive imaging. That is to say, we want to put the source and the receiver in same point and use the receiver to record the energy generated by the source, and we can directly get the seismic imaging based on what we record in the receiver without further processing. That's our ideal situation. In real, it's not effective and efficient if we do like that. In real project, we use multiple receivers to record data from a shot, and data are generally gathered in shot together, like this figure. So directly, we cannot directly get the 0 meters offset data. Here is the equation for the travel time of the reflected waves, and it is also hyperbolic curve. Here's the shot gather record. We can see there are straight line and curved line. That's also the typical types of the waves, and the reflection of the layers underground is their curve is like a hyperbolic curve. It's a weak signal in the shot gather record. Here are the general procedures we used to process reflection data. First, we prepare the data, like cut off the dirty data, gain adjustment, statistics correction. And also, after that, we do deconvolution. That is used to increase the vertical resolution. Then we do velocity analysis. That is to find a proper velocity to correct the trace travel times. Here is used for us to get that 0 meters offset reflection data. And at the last, we called NMO, normal move-out correction, and then stacking to image the subground. Here are the static corrections. In this process, we use the reflection tomography result as a PV velocity to correct the raw data. Here, the line ups after the correction of the statistics, the lineups look like the straight line. That's the ideal situation. Then we do velocity analysis. Velocity analysis is to find a specific velocity of each steps to line up the reflection lineups. Here is the final result of NMO. We can directly see the layered model of the Earth. Here is the comparison between reflection and the refraction. There are many differences between them. Typically, I want to mention here the vertical resolution and lateral resolution. They are different, and also maybe we concern most is their relative cost. The reflection is cost much. It can be 3 to 5 times of the cost of refraction method. So refraction method is more suitable to some small some small project with limited the cost. But if you have enough money, you can do reflection exploration. Here's an example to detect the Here's an example to detect the fault zone in Beijing. We can clearly find out the fault zone structure underground. This is my next part is about the structural health monitoring. Nowadays, with the rapid development of the cities, we have many big structures like bridge, tall building, and the monitoring of their health is quite important to the governors. And structural health monitoring involves the observation of and the analysis of the system over time, using periodically sampled response measurement to monitor the changes to the material and the geometric properties of engineering structure, such as bridges and buildings. Typically, the resonant vibration is the main hazard to the tall buildings. And here we can calculate the resonant period of a structure. Here is the formula we use to calculate the resonant period of clock pendular. And also we can deploy the sensors in the building to record the to vibration data, and we will use the sensor data to analyze how the structure be influenced, how the structure vibrate. So we can get we have 3 aspects we can derive from seismic data: power spectral density, and second is the seismic interferometry, and third is HV ratio. Here's a real example conducted in Shanghai Tower. The Shanghai Tower has total height of over 600 meters, and it has over 100 floors, and the stations are deployed in each layer. The researchers calculate the PSD power spectral density to find out the resonant period, and that's according to this equation. We can see from the figure that the blue line, the peak value of the line means that is the resonant period, where the resonant period lies. Here's the HV ratio. Also, we can conclude which frequency is most vibrate for the structures, and also it helps us to identify the resonant frequency. Here is the impulse response function of different modes. Based on the seismic interferometry, we can get the impulse response function of the building, and that function is quite useful for us to identify how the wave propagates through the building, assuming that the pulse in impulse impact implanted on the building. We can see the shear wave propagation and P wave velocity, P wave's propagation is quite different. Here is the vibration modes with under different frequency, from low frequency to high frequency, and we can see the vibration mode clearly shows how the building vibrate. So what can we get from the Seismic method for the structural health monitoring? Ground vulnerability, individual building structural vulnerability, and side effect, vibration modes, propagate wave velocity, rotation, and twist. All these properties we can get from Seismic methods. All these properties provides a thorough understanding of the state of the structure through time. Here's my last slide, a summary. Today I show three Seismic methods to do investigation to the soil property. For surface wave method, we can get S wave velocity model, and that's directly related to the soil stiffness. For the refraction method, we can get P wave velocity, and that can be helpful for us to get the information about the water saturation, such as the information. And the last refraction method can help us have a detailed understanding about the layered structure of the Earth, and that help us identify the faults underground. And also for the structural health monitoring, we can get the natural frequency, and also we can get the vibration modes of structure, and also stiffness of structure. All these parameters we can have more detailed understanding about our tall buildings, and that's quite fundamental material or materials for the for the researchers to do further decision or further determination to the buildings when the hazard happened to the structure, to the buildings. That's all. Thank you for the listening, and I will thank all the people for their work for today's activity. Let's have a 5 minutes break, 5 to 10 minutes breaks, and then our next presenter will give our applications introduction. That's all.
Oke, Pak and tim. Pak Sadar, mungkin apa mau terima pertanyaan dulu atau gimana?
Ya Pak, terima pertanyaannya, dibacain.
Hello,
Saya bacain Pak.
Are there any questions for me?
Okay. Okay, Mr. We will ask you some question from these attendees. Please listen this question, okay? Maybe you can ask after I tell the question. Okay, the first question is from Lely Marini. What soil conditions are we required to test for liquefaction?
Actually, there are many aspects we can use to evaluate the liquefaction potential of the soil.
Sorry, Martin, sorry. Martin, sorry.
With the method I mentioned in the slides,
Martin.
the author used 4 parameters to do the prediction of vulnerable area. And there's one parameter we can use, which can be get from seismic method, is the SV velocity. And SV velocity is directly linked to the soil components. Yeah. Actually, you can search the papers. There are many methods for us to calculate the soil liquefaction potential.
Hello, Alensu. Sorry, maybe one of you have several microphone maybe on at the same time.
Please, I will prepare for the
earphones. Of some of only one, and another should be mute. If there is close a laptop, okay. Please test your voice first.
It's not clear.
Okay.
Wait, hello.
Yeah, much better now. Lanjut Pak Sadam.
他不是那么近，他那么说我能听见。So basically, there are different methods in different fields for the civil engineering and seismic engineering. So what we can get is from seismic engineering is that we can get the SV velocity, and that's a typical parameter linked to the compactness of the soil, and also we can calculate the shear modulus of the soil, and that's directly reflects the situation of water saturation of the soil. That's all I want to answer for this question. Okay.
Okay. Another question is, how accurate is the liquefaction test result, and are there any factors that affect the test result?
Okay, I got the question. For the example I just mentioned in my slides, that in that research, the accuracy is about is around 80%. It means that the author with the author's method, it can predict where for 80% of the area. It's used comparison. 他能看见我的屏幕吗? Yeah. If you can see my screen, like for the comparison between the two figures, as the researcher successfully predicts the vulnerable area with his method. Yeah. So the accurate is actually, it depends on the parameter you used, how accurate the parameter you used, and the typical empirical equations you invent. Yeah. So there are many empirical equations the researcher used to predict the vulnerable areas. So what I use here is according to a researcher from China. Their paper published in 2020 in CGG. Yeah. So typically it depends on different situation, but I think the accurate rate is about 70 to 80%. That's all.
Thank you. There's another question from. Wait a minute.
Excuse me, Sudan. Excuse me. Hello, Sudan.
Yes.
They have another presentation on the project case from Wei. So shall we just to answer the question after the presentation from Wei? So they were just to save some time.
Okay, so go ahead.
Okay. So let's just start the second presentation at first. Okay.
Okay.
So any more questions? You can just send a message on Zoom.
Okay.
And she will just keep answering online. Okay.
Okay. Now it's case study, ya.
Yes. Thank you.
Okay. Wei Hong Yu will present the case study.
Yes.
There are some case study. Jadi ada beberapa case study yang menarik sekali buat bapak-bapak yang mungkin ingin tahu ya bagaimana pemanfaatan alat ini ya sama analisisnya.
Okay, so shall we start now?
Okay, please start.
Okay, thank you.
Hello, can you unmute your Zoom? We can hear your voice.
How about now?
Yes,
No.
we can hear.
Yeah.
Please.
Better? Okay.
Yeah,
I will bring the microphone closer.
Sorry, but the voice is not good. Please check again.
Yeah, hello?
Maybe not
Can you
good,
check?
not really good.
Not very good.
Maybe use the same microphone like before. Alan's.
Okay.
Yes.
Hold on.
Okay. Jadi kita akan ada beberapa case study ya di oil and gas, coal mining, geoteknik, engineering, scientific application. Nah, ini menarik sekali. Ada banyak hal yang mungkin bisa menjadi inspirasi penelitian ya buat bapak-bapak ibu. Sebagian memang profesor, doktor, saya lihat ada pertanyaan-pertanyaan susah nih. Mungkin nanti dijawab ya sama rekan-rekan engineering dari DTCC nanti. Yes, please.
Okay, so let me try again.
Yeah, but the voice is not so clear, sir.
Is that okay now?
Still not good. Still not okay.
Not good?
Alan Su used to be
speak.
better. Okay. Test. Please test again. Your voice.
Hello?
Maybe too close, maybe.
Hello? Okay. I live a little far away. Is that okay?
Yeah. Much better.
It's okay now.
Yes, that's good.
Okay.
Please.
I will start from beginning again. Yeah. Good afternoon, everyone, and thanks for coming this webinar, and thanks Testing Do for hosting this webinar. My name is Malin Wei, and I'm the technical support of Smart Solo. And today I will share some cases that conducted by our customers, and I have split these cases into the following subtitles. And the first oil and gas engineer case is called Smart Solo conquired. Sorry, something just stopped my. Okay. First case called Smart Solo conquired a seismic forbidden area in China. And we call it forbidden area because the terrain is really rough and dangerous here. And it brings a huge operation difficulty for the crew. Considering about this condition, the crew decided to use Smart Solo in this rough and dangerous area because it is cable free and use their old cable system in the flat area. And from these pictures, I think you can see how crazy is this place. And you will find a helicopter here because the helicopter is in charge of transport people to the unreachable positions. Even in this rough and dangerous area, Smart Solo also guarantees very good data recovery rate. You can see the designed receiver points are more than 150,000. We still give the data recovery rate more than 99.60%. And here is the combined shot gather with Smart Solo and cable system. And you will see the data combined very well, and no phase delays, no time delays. And the client estimated that the project would be taken more than 100 days, but the crew finished this project in 60 days, which they can save more than 40 days costs. If you compare with the historical projects, the efficiency increased about 70%. And the second case is from Australia. A new technology called compressive sensing is applied in this project. Compressive sensing will allow the crew to acquire very high dense data, but with a small count of devices. The source and the receiver intervals are not fixed. It's randomly from 4 to 16 meters in compressive sensing project. I said randomly, but actually it's calculated. If you use traditional reflection method, the source and the receiver interval usually fixed. And as you can see, if you use traditional method and you want equal high dense data, you will need 3 times more devices. But so that's how the compressive sensing can save your cost. And Smart Solo gets very good feedback in the use, as it's cable free and easy to deploy and have very good data quality and high reliability. Especially it's very flexible, so make it very suitable for compressive sensing technology and other new technology in the future. And here's a stack section, and you can see here's the reflection interface very clearly. I know you may not be interested about oil and gas explorations, but what I want to express from these cases is that the seismic instrument technology has improved a lot in terms of efficiency, cost saving, flexibility, and data quality. And these features are also very important in engineering applications. And the next title is coal mines and geothermal resource exploration. And when we talk about these explorations, they use similar method. They use active source reflection method, similar as the oil and gas reflection, but just in smaller depths and scales. So I prepared some special cases in passive method. And the first case is shared by AMS. It's one of our clients in Australia. IMS is an institute that's studying the seismic rock mass response for mining. And they are very good at using passive method to investigate the underground structures. The passive method uses the ambient noise from everywhere, from any sources, such as motor vehicles, like tides or wind, blah, blah, blah. In field, we just, like the picture, we just bury nodes underground to get better data quality for better coupling and to reduce the wind noise. But somewhere digging a hole is not allowed, so the node can be knocked into the ground. If you compare with passive seismic and passive seismic, I mean active seismic and passive seismic, the passive seismic will generate a 3D velocity cube or 2D profile, but active source seismic only imagining horizontal or sub-horizontal impedance contrast. So as you can see in the picture, you can find some vertical structures from the velocity profile, but nothing shows here in the active source section. By the way, the cost of active source is more than 10 times of passive source, and that's why MS choose passive source, and they believe the passive source will be the seismic future. Okay, here's another case. We use microtremor method for geothermal exploration. In this case, our customer used 48 devices and deploy a linear array. Each device distance is about 150 meters, and the total line is about 6,000 kilometers. Sorry, 6 kilometers. And the recording time about 5 hours. In these 5 hours, this station record microtremor data, and from deploy to retrieve all the devices, the job finished in 1 day. And here is the profile of the passive data of the shear velocity. Combined with the drilling data ZK1 and ZK2 and their MT data, there are 5 faults are interpreted. And we can see the velocity altered on each side of the faults. So they believe this is a fault and caused by the velocity abnormal. And the next case is fracturing monitoring of geothermal production. I'm not sure if you remember in 2017, there was a serious earthquake disaster in Korea, South Korea. And people injured and property is lost. And there was the first earthquake and then another earthquake followed. And there's a saying that the second earthquake is caused by fracturing during geothermal production. No matter it is true or not, after that, more and more attention are paid to fracturing monitoring. And when we talk about monitoring, it always means real time or near real time. So in this case, a new generation of smart solo product called IMU was applied. And this product equipped with mobile network module, and which allowed this device upload the data to cloud server in real time. So, and these devices are radially distributed around this fracturing well. According to this data record, there's another third-party program identify these microseismic events. There are thousands of microseismic events occurred during hydrofracturing, and this program identified these events and positioned on the plot. And this result will guarantee the fracturing production work effectively and safely. Okay, next subtitle is engineering, and I will share more details. The first case is a viaduct pier foundation investigation. As you can see on this map, there was a port, and there will be a new railway built from the port to inland for cargo transportation. Before that, our customers are required to do some foundation investigation. Their first priority method is drilling. But as you can see, there's a farmland area, and the drill is not allowed here. So they decide to use a flexible geophysical method in this area. As the macro tremor method has become more and more popular in China, the customer found us for devices and tell us they will try macro tremor method here, but they still leave some drill holes for data quality control. And their target depth is about 70 to 80 meters. So we provide them 24 devices, and they split these 24 devices into 2 groups. And each group is arranged with irregular L-shaped array, like here, L-shaped array. And the station interval is about 5 meters. And each array record 20 minutes micro tremor data, and then it can be moved to next position. So here, each array will provide a one-dimensional vertical result. And if you connect this one-dimensional vertical result, you will get a 2D profile of shear velocity. For example, here you can see low velocity abnormal. So I think the customers must be very careful with this area. And the second case is using micro tremor method for gulf area detection. Let me introduce the background first. There was a land subsidence occurred beside the highway 5 years ago, and there was a natural gas pipeline across that area. So the related organization asked our client or customer to conduct some geophysical survey to monitor the underground variation. And our customer tried the electrical method, they tried MT, and they also tried active reflection or refraction. But the MT result only reached the top part of the abnormal zone. So they want to use another new method. As I said, the micro tremor become more and more popular in China. So they find us and contact us for devices for micro tremor. And the reason of the subsidence has been improved as there was a gulf area collapsed beneath this place. The MT result only see the top part, but unable to go deeper for the bottom parts. So they tried micro tremor method. And we provide them 10 devices, and these 10 devices also arranged with an irregular L-shaped array, and the station interval is 8 meters this time because they want deeper, so the array size will be larger. And the recording time also 20 minutes for each position. Here is a profile along the gulf area. And as you can see, the land subsidence here, and the near surface shows low velocity abnormal. Also, the gulf area and the mining roadway shows low velocity abnormal. But if you keep going deeper, the velocity increase normally. So here is the bottom of the collapsed zone. And this is another profile across the gulf area. And there is a low velocity round abnormal shows here. And this is the gulf area. Next case is looking for a cluster cave in urban city. In urban city, there are many human activities. And in urban city, they are full with electromagnetic interference that will affect your affect a lot of geophysical methods such as electrical, like a magnetic method, and even GPR. You will get a bad data quality. But also for the active seismic, this you can see the pictures, the vehicle moving and the people around here is also the noise for active source seismic. But these human activities become very good source for passive seismic. So the customer use passive seismic, and they separate 24 devices into 4 groups, and each group is arranged with a pentagon-shaped array and 1 in the center. So 6 devices, 1 array. They can do 4 arrays at the same time. Station interval is 3 meters, and position interval is 5 meters, which means that they are looking for some shallow place, maybe just 10 to 20 depths shallow. And here's another classification of rock and soil layer table. And we can find the relationship between lithology and shear wave velocity. And this will help us to interpret the profile. And here are 2 profiles shows here. And the blue color means very low velocity as the sedimentary cover. And under the sedimentary cover, you will find some light blue, which is a low velocity abnormal. And the customer just marked them out as suspected crust decay. And case number 4 is a little special. And they're looking for the civil air defense engineering, and which is similar as a void underground. And the customer contact us they are carrying out a project, but there was a known air defense engineering position. So they want to do some micro-tremor survey line for test, for verify this method. And we provide them devices, and they tried two kinds of arrays. They tried the triple triangle arrays, and also tried the linear arrays. And both the array, result of the array shows low velocity abnormal at the same position. And that's exactly where the air defenses engineering are. And case 5 is railway subgrade inspection. When we were inspect railway subgrade, your target may be very shallow and you want very good resolution. So the customers decide to use MASW method, and which is also an active source method. And you can see there's a guy holding a hammer like the active source. And these receivers, these devices, is waiting for the trigger of the source and receive all the vibration after this guy hit the ground. And then we can get shear wave velocity from these records and make a profile. And we can find a low velocity abnormal here, and this is a visible railway culvert. And the other place looks very flat. And except these engineering or exploration cases, we still have some scientific researches, which is really interesting. And the first case is estimate of seismic vulnerability in South Korea. And there's a town of Hainam in southwest Korea, lies patrol on reclaimed coastal land and experienced an unprecedented earthquake swarm during April and May 2020. You know, the town was destroyed somewhere, and the government want to rebuild some new district. But to evaluate the seismic vulnerability is very necessary before they rebuild towns here. And our customers decide to use microtremor horizontal to vertical spectral ratio, which is H3SR method, to identify resonance frequencies and image depths to bedrock. Then they can assess seismic ground vulnerability in this area. And H3SR require 3-component devices, so they use the IGU 16HR 3-component. And as you can see, they distributed devices in this area. And after a long time, microtremor data acquisition, they can do some data processing and extract H/V curve from the microtremor data. And here are 4 figures shows different types of the curve. And the first one is a single peak, and second one is multiple peak, and the third one is a single peak but higher frequencies, and the last one there's no peak. And the frequencies at this peak is the fundamental resonance frequencies that we are that we want to get, that we want to investigate. And according to the resonance frequencies, we can calculate the depth to bedrock in this area. And we input this depth to a program, and with a lot of parameters, we can calculate the ground shaking vulnerabilities. And as you can see, the blue color means low vulnerabilities. So the government planned to create new towns here, and here. So that's all for this case. And another case is from Singapore. During COVID-19 lockdown in 2020, everybody stay at home, try to stop the spread of the virus. And our customers from National University of Singapore try to deploy 2 seismic sensors here and here, and try to investigate urban city activity changing. One here and one here. And this is a 60 seconds record from the sensor. And we can see the amplitude jump high here and here, and they marked 2 red dots here. And this is identified as vehicles going closer and then moving out, going closer and moving out. And in the orange box, we see a lot of peaks here, and it's recognized as a runner approaching and then going far away. And here is the time frequency analysis of this data. It also shows same features. Now we have all the data analysis of the north sensor. And the green, the color means motor vehicle counts. And here you can see weeks in CB and weeks after CB. CB is short for circuit breaker, and the Singapore government called the lockdown time as sticker. So CB is actually is weeks in CB. So right color after CB. So we can see during the lockdown time, people stay at home. Not too many vehicles going out, and the number decreased significantly than the weeks after CB. And there's another sensor near the port. We can see the traffic is still heavy even during the CB. And this is the runner count from the park. The runner count increased a little during CB, especially after lunchtime. After supper time. So it looks like the people realize that health body is the best defense against the virus. And that's all for today. That's all the cases. Here's our LinkedIn account. If you are interested in Seismic, you can welcome to follow us and contact us. And here sales manager's email address and technical support group email address. If you have any questions, please feel free to email us and we will reply you. And yeah, that's all for my presentation. Thank you very much again. So Martin, finish. Yes, finish. Okay, so it's question time. I think, did anybody want me answer some questions?
Ya, Pak Sadan, silakan, Pak.
Yeah, baik. Hello. There's a question from attendees. First question is from, Professor Dr. Insinyur Agus. Liquefaction depends on compactness and PGA. The question is, what are the limits for compactness and PGA values to be safe?
Please come again.
Sorry, Simon. I just turn on the volume. Can you just ask again?
Okay. This is from Professor Dr. Insinyur Agus. The question is, liquefaction depends on compactness and PGA. The first question is, what are the limits for compactness and PGA values to be safe?
啥意思？ 你来。Let's welcome Alan Xu.
Actually, I think this is a good and more practical question and relates to the PGA, the relationship between PGA and the compactness of the soil. And I think in different regions, it can be different because of the soil property. And also, as the researchers use empirical relationship in their researching area. And I think we should do more researching job about the area we are concerning. And I'm not not quite familiar with this area, and so I can't say too much about this. And maybe later I will do some research and answer these questions. And if you, I wonder if you can convenient to leave a contact to us.
Yeah, I have the contact. We will personally keep in touch with the professor after this.
Okay, thank you. So next one. Anyone else? Hello, Sadan.
Continue, Pak Sadan.
Yes. Okay. Another question from someone in attendance. How to model the soil condition after liquefaction and what software is suitable, because considering that Flexis cannot be used until the end. Moreover, the water source that cause excess PVP can be from rivers, bays, even aquifers that break when hit by an earthquake. Thank you.
Before, I think the situation before and after the soil liquefaction is quite different, and the most obvious way is to do the field survey. We can judge the condition of the liquefaction by the state of the buildings on the ground, and
and also we can do some institute test for the area with liquefaction. And so the software, I think I haven't found any software specific doing the liquefaction, but I think from the requisition of the researching papers, and it's quite easy for us to do some programming in language to calculate
Dia juga lupa linknya nggak
even the
dikasih.
Excel can help us to calculate.
Saya tunggu bentar, Mas Yunan baru dari ruangannya GM. Dia juga lupa linknya nggak dikasih.
And it's all very stable.
Okay, thank you. Another question is from Andri. If an area has a potential to experience the liquefaction, can this tool or can this smart solo be used as a basis for mobilizing the community to a safer area?
I'm not quite clear about the question. Is that to say if we provide the community service, right?
Yes, it's about the if one area has a potential to have a liquefaction, can these smart solo tools can be used as a basis for mobilizing the community to a safer area, or can detect in early state?
Yeah, I think smart solo can be a way for the engineers to do some research on some area which is prone to be liquefied. I think the SY velocity is a good parameter for us to evaluate the vulnerability of the area. I think my answer is yes. Smart solo is I think it's a good cost-effective way to do research of. For example, if we do a survey with dozens of stations and also with active methods, it's quite simple and efficient for us to evaluate the area to see if it have potential to be liquefied after the earthquake. And also, what I mentioned in my slides, that actually we can find many empirical equations invented by some researchers to help us to predict the vulnerable areas, and also some details we can get from open resources, and also combining these parameters and also with results from sensing methods, we can have a better understanding about the areas that we are concerning about their soil quality in terms of the liquefaction. That's all.
Okay, thank you. The next question is, I think it's a live question from, maybe the first one is Mr. Muhammad Taslim. Maybe you can ask the question by open your microphone. Thank you. Mr. Muhammad M. Taslim, can you speak right now? Or
Pak Taslim, silakan Pak, yang mau langsung tanya boleh.
Okay, if Ms. Taslim can join right now, maybe we can ask Mr. Robinson. Maybe you can open your microphone and ask the question.
Ada yang mau tanya langsung Pak, silakan Pak. Pak Robinson boleh. Yang mau tanya langsung silakan raise hand ya. Mungkin Pak Sadan ya, karena memang pertanyaan-pertanyaan ini mungkin ya kita ini ya. Udah semua terjawab? Kayaknya belum ya.
Udah ada beberapa, ada yang ditahan Pak, yang tadi diskusikan. Okay. Maybe another question from the Q&A box. This is from Said Buhari. How large area should be sensor be installed to find out the soil condition?
How large what? Pardon?